Our speaker today is Miklós Bóna, and he will be talking to us about permutations. The floor is yours. Thank you.
Thank you, Sandra. I will give a survey of the pattern avoidance problem. So for us in this talk, a permutation is an arrangement of the integers 1 through n so that every number shows up exactly once. So this is like the computer science definition, not so much the group theory definition. So for instance, these are permutations. Oops, now this I pushed I advanced too much. So let's go back. Maybe I have to stay in this. Okay, yeah. So our most important definition for the rest of the talk is pattern containment and pattern avoidance. So if you came with the idea that you will pay attention for 5 minutes, then please make it these 5 minutes. Otherwise, you will not have a choice. So a permutation contains a shorter permutation if there's a subsequence of entries in the long one, which relate to each other as the entries of the short one. So one picture is worth 10,000 words. Here is an example. Oops. See, the long permutation P contains the short permutation Q equals 1, 3, 2. Because you can find 3 entries in the long one, those 3 that I marked red, that relate to each other the same way as the entries of the short one, namely that the first one is the smallest, just like in 1, 3, 2, 1 is the smallest. The second one is the largest, just like in 1, 3, 2, the second one is the largest. And the third one, 6, is the middle one in size, just like in 1, 3, 2, the last one is the middle one in size. So therefore, we say that this P contains the pattern Q equals 1, 3, 2. This is the definition of pattern containment. Is this clear? So you have absolutely no doubt whatsoever at all, right? Okay. That's not how you do it. So let's see if I can do it this way. Yeah. If P avoids a pattern, if P doesn't contain Q, then we say that P avoids Q. Okay, so a long permutation either contains a smaller pattern, or if it doesn't contain it, then we say it avoids it. Let F and Q denote the number of permutations of length n that avoid the given pattern Q. Then there are 2 major directions for research. The first one is how large is this number? And there was a conjecture from 1980 by Herb Wilf and Richard Stanley saying that this number is very small, meaning that for every pattern Q there exists a constant CQ that depends only on Q, not on n, so that this number of permutations of length n that avoid Q is at most that constant to the n. So that the conjecture is very ambitious, right? Constant to the n is like nothing compared to n factorial. And that's why it was so hard to prove it, because the usual methods like probabilistic method are just not fine enough. Closer to the end, like in 1999, it was almost proved by Noga Alon and Ehud Friedgut. But by almost, I mean that they proved that this number was less than a constant to the n times an extremely slowly growing function, a function that grew slower than the inverse Ackermann. And some people then theorized that maybe the conjecture was actually false, and instead that almost version was true. But it turns out that no, the conjecture is true, and it's proved in an absolutely beautiful paper by Adam Marcus and Gábor-Tardos in 2003. If you take away all the preparations, then it's just 1.5 pages of a wickedly well done pigeonhole principle. Okay. So the other main direction of research is how nice is this function, this is the sequence of numbers of permutations avoiding a given pattern Q. And there was a conjecture there by Doron Seiberger and his student John Noonan, which said that this is a very nice sequence, namely that it's polynomially recursive in n. That is to say that the number of these numbers satisfy recurrence relation, so you can compute the nth member of the sequence from the preceding k members from some fixed k as a linear combination, so that the coefficients in the linear combination are polynomials. Now, as much as I know, Doron doesn't believe that this conjecture is true anymore. So his conjecture is now that these sequences are polynomially recursive, or maybe not. Also, Doron and his student Noonan conjectured this not just for a single pattern, but also for the more general problem of what if you want to avoid not just one pattern, but a set of patterns. And that, in that general sense, the conjecture is false, as it was proved by Igor Pak and his student, then student, Scott Garabrand. But it's a huge set that they need to avoid in order to have a counterexample. So for single patterns, it is still open. There are the problems are generally pretty hard. There are two special cases where it's not so hard. And one of them is monotone patterns. So let Q be the monotone increasing pattern 1 through K, 1, 2, 3, all the way up to K. In that case, it is easy to prove that the number of permutations avoiding that pattern of length n is at most k minus 1 to the 2n. So in that case, that constant CQ is k minus 1 squared. And here is how you do it. Take a permutation that avoids the monotone pattern and define the rank of each entry. The rank of an entry x will be the length of the longest increasing subsequence that ends there, okay? And here is an example. Here is my pattern P, my permutation P, and the rank of the first entry is, of course, 1. The rank of 8 is 2 because it's the longest increasing subsequence that ends there is 6, 8, and that has length 2, and so on. So I define two words. Maybe on my next slide. Yeah, I define two words. The first word is the rank of the first entry, the rank of the second, the rank of the third, and so on, the rank of the last. And my second word is the rank of the entry 1, wherever it is, then the rank of the entry 2, wherever it is, and so on. Now, clearly, if my permutation avoids the monotone pattern of length k, then these numbers are between 1 and k minus 1 inclusive. Oops. So the number of these pairs of words is at most k minus 1 to the 2n. On the other hand, these words completely determine the permutation, right? Because crucially, ranks, the entries of the same rank must form a decreasing subsequence, right? That follows from the definition of the rank. If you have two entries of rank 6, then the one on the right has to be smaller, because if it was bigger, then it would be of rank 7, because it would have an entry of rank 6 on its left, which is smaller than. So therefore, you look at these two words and you say, well, I know which entries are of rank 1. Let's say entries 1, 6, and 15 are the entries of rank 1. So I put them in decreasing order, 15, 10, 1. And then I look at the first word, and from that I figure out where these entries should be. Where are the number 1s in this word? Okay. So therefore, this pair of words completely determines your permutation, and the number of these words is at most k minus 1 to the 2n. So the number of permutations avoiding the increasing pattern of length k is at most k minus 1 to the 2n. It turns out, it's much harder to prove, that it turns out that this crude proof argument is actually, it gives you the optimal exponential upper bound. So the truth is actually k minus 1 to the 2n over a polynomial over n to something, n to k square minus 2k over 2, but that doesn't matter. But so you can't improve on the exponential. So I said there were two easy special cases. One was that I just said, the monotone patterns, and the other easy special case is very short patterns. By very short, I mean 2 or 3. So of course, if you want to avoid a pattern of length 2, then you can't have an increasing subsequence at all. So There's only the decreasing permutation that is like that. And also the same for if you want to avoid a decreasing pattern of length 2. How about length 3? So these two chains of equalities are obvious, because if a permutation avoids a pattern, then the reverse of the permutation avoids the reverse of the pattern, right? And also you can turn the permutation upside down. Like if it's a permutation of length n, then you can write n plus 1, n plus 1, n plus 1 over each entry and subtract them. So you replace the entry pi by n plus 1 minus pi. That's called the complement of the permutation. And then if p avoids q, then the complement of p avoids the complement of q. So this is true, and then again you do reverse, so this is true. Similarly, this is true, you can do either reverse or complement. But that raises the question whether these four are equivalent to these two or not. By the way, yeah, we call them Wilf equivalent if they are avoided by the same number of permutations of length n for every n. That those two are equal is not trivial. That's the first non-trivial result of the subject, but it's true. Now, I will show how to do it because it will be helpful later, and also it shows what the early methods were in this field. So this is due to Rodrika Simeon and Frank Schmidt from 1980. And again, it will come in handy later. So a left to right minimum in a permutation is an entry that's less than everything on its left. And now let us classify permutations of length n according to the set and position of their left to right minimum. So two permutations are in the same class if they have the same left to right minima and they are in the same positions. And now I will prove that each such class contains exactly one 1, 2, 3 avoiding permutation and exactly one 1, 3, 2 avoiding permutation. Hence, the number of permutations avoiding one or the other has to be the same. Again, one picture is worth 10,000 words. So how does a 1, 2, 3 avoiding permutation look like? These red entries are the left to right minima. By definition, they are always in a decreasing subsequence, right? Because they, by definition, have to be smaller than everything on their left. The blue are everything else, all the entries which are not left to right minima, okay? And they have to be in decreasing order too, because if they were not, if there were two blue entries in increasing order, then you could take those two and you would go to the closest left to right minimum on the left, and you would have a 1, 2, 3. Okay, so once you know the set and position of the red entries, the left to right minima, you know everything. You have no choice but write everything else in decreasing order in the remaining slots. So this was kind of a global organizing principle. So to avoid 1, 3, 2, you need to think more locally. So you again take the left to right minima, which are, the set and position of them is the same as above. And now you want to fill the empty slots with the remaining entries so that you don't form a 1, 3, 2. And I claim that there's only one thing you can do, and you can always do that. Namely, to every empty spot, you go left to right, and to every spot, you put the smallest entry that's eligible to come there. By eligible, I mean that it will be bigger than the closest left to right minimum on the left. That has to happen, right? Otherwise, this would also be a left to right minimum. And so why is it that you have to do this? Because if you didn't place the smallest eligible entry that could come here, you wouldn't place that first, then that entry would come some later time, and then it would form a 1, 3, 2 with the closest left to right minimum and the entry that you placed in its stead. Okay, so this proves that these two numbers are the same, those that avoid this and those that avoid this. Those are the same, but what is that number? And those are the famous Catalan numbers, right? Because it's easy to see that, well, these numbers satisfy this famous Catalan recurrence relation, right? Because you place the entry n first, and then everything before n, and it has to be bigger than everything after n, otherwise you get a 1, 3, 2. And so therefore you have no choice for the set of entries that come before n or after n. Yes, and on the other hand, before n, you have to have a 132 avoiding permutation, and after n, you have to have a 132 avoiding permutation. That leads to this recurrence, which you then solve and you get the Catalan numbers. You see that we know that the Catalan numbers are 2 n choose n over n plus 1. So in particular, this number is less than 4 to the n, but the constant 4 cannot be improved. Again, as we already knew, because for the monotone patterns, I already said that the constant for monotone patterns of length k is k minus 1 squared. So in this case, k is equal to 3. So again, you get 4 to the n as you should. Okay, so this is where the easy part ends. When we go to patterns of length 4, then a miracle happens. There are 24 patterns of length 4, but it turns out that, and I will talk about that later, only 3 are really different. But those 3 are really different. This line is extremely exciting. There are 2 miracles here. Well, the first one is that those numbers are not the same. So for length 3, they were the same. For length 4, they are not the same. And second, note that the monotone pattern is at neither extremity. It's not the easiest or the hardest to avoid. And that's rather unusual, right? Unexpected, because the monotone pattern is so special. So you would think that it's either very easy or very hard to avoid. It's extreme in many ways, but not here. Any other pattern of length 4 is equivalent to one of the above 3. So we already said that there are these trivial equivalences, namely taking the reverse or taking the complement. There is a third one, the group theoretical inverse. So that's the only time in this talk that group theory comes in. But if P avoids Q, then the inverse of P avoids the inverse of Q. Essentially, you can think of permutations as matrices and then think of transposes. So there are these 3 trivial equivalences, and then there are some non-trivial ones. There are some equivalences that have to be proved, and they're not easy. But using all that, you can prove that these are the only 3 different cases, but as you see, it's very different. And it will get even more unexpected than this. So for the monotone pattern of length 4, Ira Gessel proved this formula. This was not the original form in which he proved it. His original form was not this nice because it involved an alternating sum. But 7 years later, he modified it. So now all the summands are positive. The proof is not easy. It uses symmetric functions. I proved it in my thesis that this was the formula for 1342. Now, there are 2 surprising things about this again. One is that for my pattern, 1342, the exponential order is 8. These numbers grow roughly like 8 to the n, whereas for the monotone pattern, 9 to the n. So not only those 2 sequences are not equal, but they are really not equal, right? The ratio goes to 0 at an exponential speed. Okay, so they are really different. And the second difference is, so in particular, k minus 1 squared is not always the best constant, not for every pattern of length k. It can be proved also that my generating function is algebraic, but that of Ira Gessel is not. Essentially, well, it doesn't grow in the right way. It's an exponential over a polynomial, and that cannot be algebraic. Whereas mine is an exponential over n to the 2.5, and that can. And it is, in fact. So the monotone pattern is not the nicest. It's not only not the easiest or hardest to avoid, but it's also not the nicest in terms of leading to a nice generating function. Okay. Now, how about this last one? This is very difficult. Doron Seilberger once said that even God doesn't know what the number of permutations avoiding this pattern that are of length 1000 are. We don't even know the exponential order. And I will show some selected results later. And it turns out that this is not the only aspect from which this pattern is difficult. So I proved in my thesis again, that's an early result, that these numbers are always bigger than those numbers. And I will show this proof even though it's like 28 years old, but it's a nice proof. It brings a flavor of algorithms into this talk. Maybe that will be the only time I talk about algorithms today. So I define left to right minima before, and I define a right to left maximum. It's an entry that's larger than everything on its right. And then let's say that two permutations are in the same strong class if they have the same left to right minima and they are in the same positions, and the same right to left maxima, and those are in the same positions as well. So for instance, these two have two left to right minima, 3 and 1, they are in the same positions. Two right to left maxima, 7 and 5, and those are in the same positions. So these two permutations are in the same strong class. Now I will show that every strong class contains exactly one permutation that avoids 1, 2, 3, 4. But at least one permutation that contains 1, 3, 2, 4. That will prove the weak inequality, and then it will be easy to see that at least one will mean more than one at least once, and that will prove the sharp inequality. So the first part is easy, right? If you have the red entries fixed, the left to right minima, and you have the blue entries fixed, the right to left maxima, then there is only one thing you can do with the remaining entries, the green entries, namely you have to write them in decreasing order in the remaining slots. Because if you do anything else, if you have two green entries in increasing order, then you go to the closest left to right minimum on the left and the closest right to left maximum on the right, and you have a 1, 2, 3, 4. Okay, now how about the other one? Let's say that you take a permutation. Again, the red guys are the left to right minima, the blue guys are the right to left maxima. And let's assume that the permutation doesn't avoid 1, 3, 2, 4. So there is a bad pattern. There's a 1, 3, 2, 4 somewhere. If there is such a thing, then it's easy to prove that there is a bad pattern where the middle guys are both green. In fact, that's the only way it can happen. So swap those two middle entries. So this 3 and 2, I swapped them. So I destroyed that bad pattern, but maybe there are others, and maybe I created new ones, who knows? So I keep doing this. And once this procedure stops, once this algorithm ends, then there's no more bad patterns to destroy. So I obtained a 1, 3, 2, 4 avoiding permutation without leaving the class because I didn't touch the red or blue entries. So the question is, why will this algorithm stop? How do I know that it stops? Any ideas? I'm asking the audience if you have an idea why this algorithm of stopping, of swapping the middle entries, why does it have to stop? Why can't it go on forever?
Maybe something about some sort of rank always goes up or down.
Or down, yeah, very
can't
good.
go up forever.
Yeah, let's find a function whose value is a positive integer, and at every move it goes down, but that can't go on forever because eventually you will hit 0. And so that function is the number of inversions, right? And the number of an inversion in a permutation is a 2-1 pattern. So 2 entries in the wrong order, the bigger one coming before the smaller one. Every time you swap these two middle entries, you decrease the number of inversions of the whole permutation. And so that cannot go on forever. Okay. So that's how I know that the algorithm will stop. So this proves that the number of permutations avoiding 1, 3, 2, 4 is bigger than the number of permutations avoiding 1, 2, 3, 4. But what about an upper bound? How many? What can we say? How big are these numbers? So I will prove an upper bound, which is no longer the best. I proved it in 2012. Then it was the best. It's no longer the best, but I will prove it because I like the proof. It's a nice proof. And also it will show you what are the kind of things that make this difficult. So there was a result from Klassen, Jelinek, and Steingrimson from the early 2010s, which proved that this number was less than 16 to the n. So note, see, this is like 8 years after the Marcus-Tardos proof. So it was very difficult to do this. And this is what I want you to pay attention to. When you hear this proof, you will say, wow, this is so wasteful. I will improve this in 15 minutes. And then it turns out that no. So I will explain why is even though it looks very wasteful, but why is it after all not so easy to improve it? So here is the proof of those three people. At least a sketch of proof, but all the important things will be there. So color the entries of a 132 avoiding permutations red or blue as follows. You move left to right. And if you colored an entry red, that would create a 132 with all red entries, then you don't do it, then you color that entry blue instead. If there is already a blue entry smaller than your current entry, then color your entry blue. And otherwise color everything red. So in particular, the first one will always be red. The second will be always red. The third one will not be red if that would create a 132, which is red. Otherwise, it would be red. And if the third one became blue, then later you can have other blues if they are bigger than the third one, and so on. So clearly, by this very first rule here, the red entries form a 132 avoiding permutation, whereas it can be shown in a paragraph or two that the blue entries form a 213 avoiding permutation. So it's not hard to prove it. It's much harder to think about it at first. So okay, so we broke up a permutation that avoids 1, 3, 2, 4. We broke it up into two substrings, one of which avoids this and the other one of which avoids that. So in how many ways can that happen? Now comes the wasteful count. There are at most 2 to the n possibilities for the set of red entries, right? Because it's a subset of all entries. And there are at most 2 to the n possibilities for the positions in which red entries are placed. So you have at most 4n choices, 4 to the n choices for completely knowing the colors of every entry at every position. Now, once you know what entry is red, which entries are red and which entries are blue and where they are, you just have to put a permutation on them. And remember, the red entries have to avoid 132, the blue entries have to avoid 213. So the number of permutations avoiding these patterns are the Catalan numbers. So if you have k red entries, you have at most Catalan k possibilities for the permutation. You have at most this many Catalan n minus k for the substring of the blue entries, and that's it. 4 to the n times 4 to the n is 16 to the n. So it's easy to say that, wow, that was so crude. I mean, I will sit down and improve it very fast because it's so wasteful, right? It doesn't use anything at all about the particular properties of these of the entries. Whereas, of course, there are certain things like, as I said, the first entry always has to be red, right? The second entry always has to be red. Every left to right minimum always has to be red, right? Because the left to right minimum will never create a 132 pattern because it can be the 2. And there will be nothing smaller than that. Okay, and so on. On the other hand, you could say that lots of things will have to be blue after you already had a blue. But here's the problem with that. All these considerations, like that the first entry has to be red, the second has to be red, the left to right minima have to be red, they will cut down on the number of possibilities, but not enough. Not an exponential, not in the exponential order sense. You can do quite a violence to a number without changing its exponential order, right? So if instead of 16 to the n, you have 16 to the n over n to the 100, that doesn't help. We want an exponential improvement. So we have to understand, we have to refine our coloring. And this is what I did. So my more refined counting argument will prove that this number is less than 2 plus square root of 3 to the 2n, which is about 13.92. Later, I improved it to something like 13.73, and then other people improved it to 13.5. So the current upper bound is 13.5. The current lower bound is something like 11. So there's still a big gap. But nevertheless, I will show this proof because this is the simplest. Note that if the square root of 3 were a square root of 4, then we would be at 16 to the n. So my improvement comes from this term. Okay, so yeah, that's no longer true. What I said unpublished is now published. As I said to Sandra earlier, I had a computer mishap and I had to use an outdated slide due to Windows 11. Okay, so let's do the coloring of entries to red and blue, as I said. But we will refine it further. Instead of just having red and blue, we will have 4 different kinds of entries: A, B, and C, and D, as follows. Every red entry that's a left to right minimum in the permutation, we will denote it A. Okay? If a red entry is not a left to right minimum, then we will denote it by B. Every blue entry that's not a right to left minimum will be C, and as you guessed, every blue entry that is a right to left maximum will be D. Okay? So now we have 4 different letters. Every entry of the permutation is encoded A, B, C, or D. And again, I will define 2 words, namely, just as before, but it's more refined. The first word will write down the type of each entry, so A, B, C, or D. Whereas the second word will write down what is the type of the entry 1, wherever it is. What is the type of the entry 2, wherever it is, and so on. So here is an example. Here is this permutation. Its red entries are those, its blue entries are those. So now let's look at the red entries, which are the left to right minima, 3 and 1. So those 2 will be A. The other red entries, 1, 2, and 7, will be B's, B, B, B. And then the blue entries in 4 and 5, out of which 4 is not a left to right, not a right to left maximum, so that's a C. 5 is a right to left maximum, so that's a D. And then here, these are the A's because 1 and 3. These are the B's because what are the B's? Those that are not left to right minimum, 6, 2, and 7. So 2, 6, 7. Then 4 is a C and 5 is a D. Okay. So here you could say, okay, so I know what you will say. You will say that these 2 words completely determine the permutation. Yes. But the number of these words is still 4 to the n times 4 to the n, you would think. So 16 to the n, so no improvement. But here is where I improve on the previous argument, namely that I will show that no, it's not 4 to the n. There is a structure which will limit it more. I claim that in these 2 words there can never be a C immediately followed by a B, which I will refer to that there's by saying that there is no CB factor. Why? This is a crucial part. So first, why does the first word not have a CB factor? Because if it did, what would that mean? That there is a C immediately followed by a B. What's a B? It's a red entry that's not a left to right minimum. So if it's not a left to right minimum, then there has to be a left to right minimum to its left. It can't be C because C is bigger than B. So it has to be something smaller. So it has to be here, right? C cannot be smaller than B because a blue entry is never smaller than a red entry on its right. So it's by definition of the coloring. So and similarly, C is not a right to left maximum. So there is a right to left maximum somewhere on its right. So there you have your 1, 3, 2, 4. Similarly, the other word also avoids 1, 3, 2, 4. Well, it also cannot have a CB factor. Okay, so now it is true that I have an injective map. I map these permutations to this pair of words. So the number of permutations is less than the pair of words. Yeah, never mind this text here. So the question is, how many such words are there? How many pairs of words are there? And that's easy to prove that the number of pairs of words like this satisfy, that they have this generating function, because they satisfy this nice recurrence relation. I mean, I'm talking about one word, sorry, not 2 words, just one word. So the number of words on the alphabet A, B, C, D, so that a C is never immediately followed by a B. Let that be Hn, then Hn satisfies this recurrence relation. Yes, because if you have a word of length n-1, then you can almost continue it in 4 different ways. You can put an A, a B, a C, or a D at the end, and that will always work, except if your original word ended in a C and then you followed it by a B. That's not allowed. And the number of those things is this. Okay? So from this, you can compute an explicit formula for the numbers Hn, and then you take the square of that, and that gives you the upper bound that I promised. So this is a better upper bound. You see there's still a waste in the method in that we treat the 2 words independently, and we just take the upper bound for the number of such word, and it's square, and then we take the square of that. And those 2 words are not exactly independent, but it's pretty hard to actually make that work for us. It's hard to turn that observation that the 2 words are not independent, hard to turn it into an improvement on the upper bound. I managed to do that and cut down the upper bound from 13.92 to 13.76. So see, with a lot of work, I didn't improve much. And yeah, so then other people cut it down to 13.5 with a much more complicated argument. The truth is not known. What about the constant? So now we don't know basically anything about longer patterns. There are sporadic cases when we know more, but not much. So it has been conjectured that that constant was at most 4 times k squared. And there was also a conjecture about what patterns will achieve that. So which patterns will be the easiest to avoid. However, that's false. So Jacob Fox, from back then at MIT, but now at Stanford, proved by a probabilistic argument that there exist patterns in Q for which CQ is exponential in K. Not polynomial like 4k squared, but exponential. His proof is an existence proof, so he doesn't actually exhibit those patterns. We don't even know what to think. So we don't have a conjecture as to which will be the pattern for which CQ will be the largest. Okay, I am running short on time, so let me just talk about this result. This is my most recent results in the field. Namely, how nice is the sequence. So when I talk about generating functions in this talk, it will be always the ordinary generating function, that one. And there are 3 classes of generating functions, rational functions, which are the ratio of 2 polynomials. The bigger class is algebraic generating functions, those that satisfy an algebraic equation, like the square root of 1 minus 4x, right? That's algebraic, but not rational. And D-finite, that means differentiably finite. That is when you take all the derivatives of your generating function and the vector space that they span over the field of rational functions is finite dimensional. So for instance, e to the x is D-finite, but it's not algebraic. Okay. So yeah, that's basically what I just said. Rational, by the way, being rational is equivalent to the coefficients satisfying a recurrence relation like that, linear recurrence with constant coefficients. And I will come back to this later. Whereas the finiteness is equivalent to being polynomially recursive. So what I said at the beginning, that satisfying a linear recurrence relation with polynomial coefficients. So here is the main thought of the last part of this talk, that when you want to solve an enumeration problem, but you can't, and you start wondering whether you can't because you're not doing it right, or because it's actually difficult. How can you measure difficulty? How can you prove that the problem is difficult other than, how can you somehow prove that it's difficult when you can't solve it? And so negative results then come in handy when you prove that you can't solve the problem, but you can prove that it's not something. And in this talk, I will talk a little bit about how I can prove that the generating functions of these sequences enumerating pattern avoiding permutations are not rational. Okay, most of them are not rational. I mean, I believe none of them are, except for 1, 2, but for most of them I can prove it. And because time is short, I will go somewhat fast. So there's some algebraic combinatorics here. So when you have a combinatorial generating function, the exponential growth rate of the coefficients is equal to the reciprocal of the convergence radius. That's a well-known fact. A less well-known fact, even among combinatorialists, is this. Well, this is a definition. Let there be two generating functions which relate to each other this way. This is very common in combinatorics. F is 1 over 1 minus g. We say that this relation is supercritical if when you plug in the convergence radius into g, you get something bigger than 1. And why does this matter? Why is this interesting? This is why. How can you get in trouble? Like, how can this ratio 1 over 1 minus gz, how can this not be analytic? There could be two things that could go wrong. Either there is something wrong within g, the g itself is not convergent, or g is fine, but 1 over 1 minus g is not defined. That is to say gz is equal to 1. So there's a division by 0. So the question is, which one happens first? If the relation is supercritical, so g at rg, g at the convergence radius is bigger than 1, that means that g was equal to 1 at some earlier time, sometime within the convergence radius. So f became singular before g did. Okay, so the convergence radius of f is less than the convergence radius of g. Hence, because the exponential order of the coefficients is the reciprocal of the convergence radius, the exponential order of the coefficients of f is larger than the exponential order of the coefficients of g. Okay. Combinatorially, what does this mean? So I just said what it means analytically, but combinatorially, what it means is that if this relation holds, then f is 1 plus g squared plus g cubed. So f can be some combined structure, and then g is the component structures. And so f grows faster than its components. So an example, yeah. Let's see another, yeah, this is better. So let f be the generating function for the number of ways to split a semester of n days into non-empty segments, and then designating each segment a day for class social, whatever. Then the generating function of g, is just this, because there is, I mean, you can compute it easily, because for every segment of length m, you have m choices. Now, f is, on the other hand, that's the composed structure, because you had the original set, you had to split it up into segments and then do the same thing on every segment. So the generating function of f is this, which is that. And what is the radius of convergence of g? 1, right? You put that into here, into you put the radius of convergence 1 into G and you get infinity, because there's a division by 0. So infinity is bigger than 1, so the relation is supercritical. So the exponential order of G is less than the exponential order of F. And indeed, you can compute the exponential order of F is 2.6. And there's a theorem that if G and F are rational, then this relation is supercritical. So if you want to prove, and this is my point here, if you want to prove that some generating function is not rational, then you can prove it by showing that this relation is not supercritical. And there you have your negative result. So you can prove that your problem is difficult in the sense that its generating function is not rational. And you know that it's not rational because it's not supercritical. Okay, and time is short, so I won't prove it, but it's easy. And so, yeah, for instance, the Catalan numbers generating function is not rational, and this relation is not supercritical. In that case, both G and F have exponential order 4, 1/4. Yeah, 4, exponential order 4, because the singularities are at 1/4. Okay, so how does this come to my goal? So I will prove that for more permutations, the sequence of pattern avoiding permutations, avoiding that pattern, is not rational. That doesn't have a rational generating function. Sorry. So I define the notion of a skew in the composable permutation. Sorry, somehow one slide is missing. Sorry about that. So we say a permutation is skew in the composable if you cannot cut it into blocks so that everything before the cut is bigger than everything after the cut. Like this one is skew in the composable, but this one is not because you can cut it after bit 5, and then everything before the cut is bigger than everything after the cut. Okay. If a permutation is not skew in the composable, then there is a unique way to cut it into in the composable strings, which I will call the blocks. Like this one has 4 blocks. Okay. So now let Q be a skew in the composable pattern that doesn't end in its largest entry, then its generating function is not rational. I will later weaken this, and we will have the non-rationality for an even bigger class of permutations. Here is the idea. If your pattern is like that, then in order for the whole permutation to avoid your pattern, each of the blocks have to avoid the pattern. And then that's sufficient and necessary. You can't start a pattern in one block and finish it another one because it's skew in the composable. Okay? And this means that there is this generating function when this is, all permutations avoiding your pattern. This is just the skew in the composable ones. So if I can prove that this is somehow not supercritical, then I'm done. And it is not, because here is the big idea. Take a permutation of length n and let it avoid q. Now put a new entry n+1 at the end. Put an entry n+1, the largest entry here. Then the new permutation is now skew in the composable because there is a n+1 at the end. There's no more way of cutting it up so that the entries before the cut are bigger than after the cut. But it still avoids your pattern because your pattern doesn't end in its largest entry. Okay? So with this trick, we prove that the number of in the composable ones that avoid Q and are of length n+1 is bigger, at least as large as the number of all Q avoiders. Therefore, these two sequences have the same exponential order because one sandwiches the other. So they have the same exponential order. Therefore, that relation cannot be supercritical, right? I said before that if the relation is supercritical, then the two sequences have the same exponential order. So the relation is not supercritical, therefore the generating function is not rational. So I can extend this method a little bit by trivial symmetries and some non-trivial symmetries, but I can extend it this much, that the generating function for Q avoiders is not rational if Q doesn't start with the entry 1 or doesn't end with the maximum entry or will equivalent to one of to a pattern which satisfies the first or the second. So the first, and note that it would be incorrect to say that it's probably true for every pattern, because if you take trivial pattern 1, 2, then there's one permutation of each length avoiding it, and so you get this generating function, and that is rational. But I strongly believe that that's the only exception, and everybody believes that. Right now, it happens that the smallest pattern for which we don't know that it's not rational is, again, 1, 3, 2, 4. See, it starts with the smallest entry, ends with the largest entry, and it's not equivalent to anything. Okay, thank you for your attention.
Let's thank the speaker. And are there any questions?
I have one question. So for this 13.5 improvement of the upper bound, does it use the same construction? And
no, it uses something else, right? But it also uses some rather heavy differential equations. So it's quite different. In their proof also, they say that there is a very wasteful element. So at one point, they just do a 2 to the n kind of thing, that here you have to choose a subset. But yeah, that proof has been out for a while, like I'm thinking 3 or 4 years, and it hasn't been improved.
I see. I think I came across a paper by Tufik Mansour where he speculates that the answer is like 11.6.
Yeah, I think a number of people think that it could be like 9 times or 8 times square root of 2, something like that. With that 8 times 1.4, that would be 11.2. So yeah, something between 11 and 12. That's what most people believe. But also, J. Pantone has very elaborate computer programs. And based on that, it seems that if it's polynomially recursive, then the degree of the recursion must be more than 500. So it's kind of, unlikely, but not impossible.
I see. And you mentioned you give some intuition why this pattern is so difficult, 1, 3 to 4. Maybe I missed that, but
no. I mean, I don't really know. But no, nobody really knows. It starts with the first entry, starts with the smallest entry and ends with the largest. That doesn't help, but that doesn't fully describe everything.
Are there any other questions?
A bit of a left field question, but I'm curious, is there any connection to something like finite automata or some device for recognizing or producing things avoiding a certain pattern?
There are some, it's stack sorting, for instance. So that the basic, the original notion from Knut, Dan Knut from, I don't know, 70s, was that a permutation is stack sortable if and only if it avoids the pattern 2, 3, 1. And in the 50 years since then, this was generalized in several ways. So yes, there are some sorting devices which work if and only if the permutation avoids some patterns.
Thanks.
One comment on that question: if there exists such finite automata, then the generating function is rational, right?
Right. Well. So that's for 2, 3, 1. So that means then the stack sorting is not a finite automata. So right, yeah. If there was a finite automata, the generating function would be rational. So these sorting devices are more complex than that.
Any more questions? Let's thank the speaker again.
Thank you.
I'll stop the recording.